Hello, LS. We arrived to the last document in our Chapter 9, Document 6, Integrating Properties of Nerve Centers. In this document, we are going to explain the excitatory and the inhibitory synapses and to make an ionic interpretation for what happens in the postsynaptic membrane. And also we are going to see how is the nervous message or the information integrated at the level of the postsynaptic neuron in the nerve centers. So in the previous videos, we have seen the structural classification of synapses and their functional classification. Today we are going to explain the excitatory and the inhibitory synapses. Excitatory synapse is the synapse that allows the transmission of the message, whereas the inhibitory synapse is the synapse that inhibits or blocks the transmission of the message. Document A represents a motor neuron and its synapses. The motor neuron, the cell body here in yellow of the motor neuron, to which is connected or are connected several nerve fibers, several presynaptic nerve fibers. So document A represents a cell body of a motor neuron in the anterior horn of the spinal cord with synapses, about 6,000. 80 to 90% of which are found on the dendrites of the motor neuron. These synapses provide the cell body with information coming from other parts of the nervous system or of the muscular system. Now, by introducing a microelectrode, ME, in the motor neuron, the oscilloscope records a potential difference of negative 70 millivolt. This is the resting potential of the motor neuron in the absence of any stimulation. Following an effective stimulation, this motor neuron responds by an action potential of amplitude 100 millivolt that is generated in the cone of implantation of the axon. What is the cone of implantation of the axon? The cone of implantation of the axon is situated near the cell body. It connects the cell body of the neuron to its axon. Now, following an effective stimulation, if the membrane polarity of the cell body exceeds the threshold of depolarization, thus the cone of implantation triggers an action potential here that will be transmitted along the axon. So only axons can form action potentials and not the dendrites nor the cell body. So the action potential is generated or originates here in the cone of implantation that separates the cell body of the neuron and the axon. The cell body will present a change in its polarity, a depolarization that when it exceeds the threshold, it creates here an action potential, and the action potential is transmitted along the axon. Now, effective stimulations are applied separately on presynaptic nerve fibers 1 and 2 connected to this motor neuron. Their recording, their corresponding responses are recorded at the level of the postsynaptic neuron on this oscilloscope. So we stimulate separately the fiber 1 and the fiber 2, and we see the variation in the membrane potential at the level of the motor neuron. We observed that the stimulation applied on the nerve fiber 1 leads to a hypopolarization or depolarization, while the stimulation of the nerve fiber 2 leads to a hyperpolarization as shown in document B. So upon the stimulation applied on the presynaptic nerve fiber, the response of the motor neuron, of the cell body of the motor neuron, shows a depolarization from negative 70 millivolt to a certain value here that approaches the threshold. So when there is a depolarization that approaches the threshold, the synapse is said to be excitatory synapse. So when the stimulation of the presynaptic neuron causes a depolarization in the postsynaptic neuron, and the depolarization, when it exceeds the threshold, it can generate an action potential. So in this case, the synapse is excitatory. It allows the transmission of the nervous message. However, upon the stimulation of the presynaptic nerve fiber 2, the motor neuron responds with a hyperpolarization from negative 70 to a certain value here. And this hyperpolarization, it never reaches the threshold. It cannot reach the threshold. So in this case, the synapse will be inhibitory. It doesn't allow the creation of an action potential. Thus, there is no nervous influx. So according to the membrane potential observed on the level of the motor neuron, we can specify the types of synapses shown here. So a depolarization means an excitatory synapse, whereas a hyperpolarization in the level of the postsynaptic neuron means an inhibitory synapse. So the excitatory or inhibitory characteristic of synapse depends on the nature of the postsynaptic receptor and the ionic channel. Here we are going to make an ionic interpretation at the origin of the formation of the excitatory postsynaptic potential and the inhibitory postsynaptic potential. If the channels that open following the fixation of the neurotransmitter on the postsynaptic membrane are Na plus channels. So Na plus will enter the postsynaptic membrane, and as you know, the entry of Na plus causes a depolarization. It always causes a depolarization. The depolarization is called EPSP, excitatory postsynaptic potential. And this EPSP, if it exceeds the threshold, it bypasses the threshold, an action potential is created, thus the nervous influx is transmitted, and the synapse is excitatory. However, if the channels that open following the fixation of the neurotransmitter on the postsynaptic receptors are either K plus channels or Cl minus channels that allow either the outflow of K plus or the inflow of Cl minus, so the outflow of K plus and or the inflow of Cl minus causes a hyperpolarization, thus an IPSP, an inhibitory postsynaptic potential that will never reach the threshold. So there is no action potential, thus the nervous message is not transmitted and the synapse is inhibitory. So this is the ionic interpretation at the origin of the excitatory and inhibitory characteristics of a chemical synapse. As you can see here, when Na plus enters, they cause a hypopolarization or depolarization. And this depolarization, if it exceeds the threshold, it creates an action potential, and the synapse will be excitatory as well as the neurotransmitter. Whereas when Cl minus enters or K plus exits, we have a hyperpolarization and inhibitory postsynaptic potential. Thus, the neurotransmitter is inhibitory as well as the synapse. Acetylcholine is an example of a neurotransmitter which is at the same time an inhibitory neurotransmitter and an excitatory neurotransmitter. Acetylcholine is found in the neuromuscular junctions. At the level of the skeletal voluntary muscles, acetylcholine causes the contraction of the muscle. So it is excitatory at the level of the skeletal muscles. Whereas at the level of the heart muscle, which is an involuntary muscle, acetylcholine is an inhibitory neurotransmitter, it blocks the muscle contraction, the heart muscle contraction. So a neurotransmitter can be either inhibitory or excitatory, like acetylcholine. Here we have some neurotransmitters and their effect. Acetylcholine can be both excitatory or inhibitory in the neuromuscular junctions. We have norepinephrine, either excitatory or inhibitory. We have GABA, which is always inhibitory. GABA, it allows the entry of Cl minus, so it is always an inhibitory neurotransmitter. We have glutamate or glutamic acid, which is always excitatory. It allows the entry of Na+. You don't have to memorize these neurotransmitters, only understand the ionic interpretation at the origin of the IPSP and the EPSP. In the next video, we are going to explain the integration and the analysis of the nervous message by the neurons in the nerve centers. Thanks for listening.